Okay, so
You're welcome.
here, I can turn this off for now. I think, okay. What do you guys know about entropy? Let's start with what you already know. And too bad Amber's not here. She's our chemistry major. She would know about this stuff.
The level of, the opposite of organization, what's that?
Okay, disorder.
Disorder.
All right, anybody heard of disorder or chaos?
Chaos.
Has anybody heard that definition?
Disorder.
Okay, it's an approximation, it's an analogy, it's not a true definition. But it's helpful, but like any analogy, you can't take it too far. Right, does that make sense? Another definition that you'll see written out is the amount of used energy, so how the quality of the energy available. Like high entropy, that energy's been used up and you can't use it for stuff. Right? So that's the idea. Does that make sense? Like gasoline is low entropy, and then you burn it, drive your car around, and you make heat, which is high entropy. So that's another definition. But we're going to give you the best definition at the end of class. We'll say that because I don't want to give away the story too soon. Okay, so how do you calculate entropy? Well, to start, when they first discovered entropy, they didn't know actually what they were measuring. They could just calculate the change in entropy. Okay? So this is the formula to calculate the change in entropy. ds is dq over t. Remember, dq is a little bit of heat, right? And dq has a line across a d. Anybody remember why? Versus ds, which doesn't have a line. A little bit of notation. P, V, T, U, N, those are all what kind of quantities? U, P, V, N, U, P, V, N, T, and then down here, Q and W. These versus these, what's the difference? Anybody remember? These are state variables. And these are non-state variables. Anybody remember this a little bit? I feel like?
Yeah, I wrote it down.
Huh?
I wrote it down.
You wrote it down?
Yeah.
So these only depend on where you are on the PV diagram. They don't depend on how you got there. These depend on the path you take. We talked about that, didn't we?
Yeah.
Yeah, so these, when you did the infinitesimal, these have just a D, and then these have a line. So you can write the first law, du is equal to dq plus dw. Yes?
Is that the only law of thermodynamics that we need to know for this test?
Uh,
I think it's the only one we talked about.
Yeah, we're doing the second one right now, in just a minute today. And the other two are easy. There's 4 of them. So the other one, well, let's just lay it out. The second law, since we're here at it, the second law of thermodynamics tells me that delta S is greater than or equal to 0 for a closed system. So entropy is going to increase. That's what it's telling you. That's the second law. Okay? So now you know 2 of the 4 laws. I might as well give you the other 2. The third law is there's an absolute 0. Right? There's the coldest temperature possible. And the first law basically defines thermal equilibrium. It says that when 2 objects right they're in thermal equilibrium, their temperatures are the same, giving me a definition of thermal equilibrium. So those are our 4 laws. But that is called the 0 law, which is kind of weird, right? So it's not 1, 2, 3, 4, it's 0, 1, 2, 3. So 0 law is thermal equilibrium, first law energy, second law entropy, third law absolute 0. So, all right, so this one. What are the units for S? Can anybody tell me?
Joules per Celsius.
Close.
Per Kelvin.
Yeah, there's no delta T. It's every Kelvin, right?
Is it for a closed system?
For a closed system. That means there's no outside influence, right? So that's kind of a weird definition. Like, I mean, okay, what did you pick up at Starbucks this morning, Mary?
It's a hot latte.
It's a hot latte, right? So that hot latte, that's losing heat to the environment, right? So if you look at just the latte, because the heat's going out, it's decreasing its entropy. Which seems to go against the second law, because it says what? The entropy has to increase. But where's that heat going? In the environment. So when you include that, when you include the effect of heating the environment, now the total entropy will increase. Right? You see the difference? So when you look at something cooling, usually you gotta look at the environment to see what's happening to get the total entropy. Okay? So that's how that works. So you can decrease entropy locally at the expense of increasing entropy in the environment. Right? Does that make sense? Okay, let's see if we can calculate some entropy changes. And in the interest of trying to get everything done, we won't work too many examples, but you can do that in your homework. I just want to give you the ideas so we can really cover all the material. So let's say I have ice, and I'm going to melt it, right? Oh, this would be an ice cube. So here's my ice cube, a mass M, and I'll melt it into a puddle of water. Okay? That's going to increase the entropy of the ice because it's got to absorb heat. Right? Does that make sense, everybody? So what kind of process is this going from here to here? Is that specific heat or latent heat? Oh, man, it's like it's Monday.
Latent?
Latent, good guess. What's latent heat? What happens during latent heat?
It changed the state.
Change my state, right? That's what I'm doing. I'm going from a solid to a liquid. What's the formula for that? Q equals what?
L.
Oh yeah, close. There's an L.
Yeah, but there's an LM.
Yeah, an L, right?
Oh yeah. There you go.
Mass times latent heat. Anybody remember this? So I can calculate the entropy change because this happens at what temperature? Ice going to water.
0 Celsius degree.
So I could calculate, I would integrate this, so I get delta S equals the integral of dq over t, but q is constant. Matthew, where'd you go?
I didn't breakfast at all today. I've been up since like 6.
Did you bring me something?
I did not.
Ah. dq is a constant. What does that mean? Right, and I make it q, right? So this would be ml over T. So that would be the change in entropy for melting my ice. Now I can't use 0 degrees Celsius. Why?
Because you can't have
Okay, it's got to be in what? Kelvin.
Carbon.
Right? So this is the entropy change when I go through a phase change. M times the latent heat divided by the temperature. Okay. And of course, if I'm giving off, right, then Q absorbing is positive. This is going from ice to water. Then Q is greater than 0. If I go from water to ice, what happens? Right? Then I'm cooling and Q is,
less than 0.
wait. Yeah, Q is less than 0. Right? Because I'm giving off the energy. Right? So the heat's going out. Does that make sense? So that would make my entropy decrease. Okay, so that's for latent heat. Let's look at specific heat. I look at specific heat, right? I have some block of mass M, and I start at T naught, and I go to T final, right? I heat the object, or cool it. Let's say we're heating, for simplicity, right? So I put in dq. dq goes into the object, and I get a temperature change dt, right? What's the formula for specific heat? Q equals
MC delta T.
MC delta T, that means dQ is equal to MC dt. Right, a little bit of heat changes the temperature a little bit. Does that make sense? So I can calculate the entropy change. Delta S equals the integral of dQ over T. And this would be from T naught to T final. dQ would be MC dt over T. T naught to T final. MC integral dt over T. Anybody?
ln
ln.
t.
Ln T. So ln of T final over T naught. That would give me my change in entropy for specific heat. Right, and this will work either absorbing or giving off or absorbing heat, right? Because then your T final flips, one's negative, one's positive. So this already takes into account the sign. All right, I don't know if this was a homework problem, but you know, what happens when I take, yes?
What's entropy again?
Disorder.
Yeah, it's entropy.
Entropy, what I mean?
We don't really define it yet.
Oh, okay.
I mean, you can think of it as disorder, randomness, or quality of energy, but we haven't really given the true definition. We're just calculating how to change it, how to calculate the change.
If it's absorbing heat, the entropy's going up.
Yeah, and if it's giving off heat, entropy is going down, because dQ is positive and negative. But we're going to define it in a minute, like the true definition, like
In a formula or?
in a formula, right? Because they don't give it to you in chemistry, they don't give it to you in biology, they lie to you. Don't tell them I said that. I'm going to give you the real definition of entropy. I always tell the truth. But this is how to calculate the change. Okay. So if you take something hot and mix it with something cold, right? So here's my cold water. Here's my hot cube. We did this in lab, right?
Yeah.
And you can calculate the entropy change. And you'll find the entropy increases, right? This entropy decreases, but the water entropy increases and is greater than what's decreasing here. Okay, so you go and you buy your hot tea, or either way, I got hot tea today, but sometimes I have icy. Was that cold?
Yeah.
It's cold? What's happening?
Right now?
Yeah, to your bottom.
Isn't it like warming up?
It's warming up.
Temperature.
Right. So it's, and yours is cooling down. So yours is decreasing entropy and that one's increasing. But either case, the total entropy is getting larger because I have to include the environment. Right? Does that make
Is
sense?
Entropy always positive?
The total entropy,
Total.
if you include a closed system, right? So Mary's tea is actually decreasing its entropy, or coffee, or whatever you made. I forget what it is. Coffee. But it's decreasing its entropy, but it's increasing the entropy of the environment more than it's decreasing.
Yeah.
Okay, that's the second law. All right, let's look at a gas process. Right, an idea of gas. We'll make it easy. In the interest of time, let's look at an isothermal process. P naught, B naught, P final, B final. Delta T is 0. This is isothermal. Let's find the entropy change. I picked this one because it's easy. Right? So, okay. What do? We want to calculate ds, right? Which is dq over t, or delta s is the integral of dq over t. So I got to find dq for this process. Okay, let's see if we can do it. So what do we know about isothermal? Somebody give me something.
Temperature's constant.
Okay, temperature's constant. I already got that. Good job. It's okay. Something else.
The change in the internal energy.
Yeah, change in internal energy is constant. But to calculate entropy, what do I need? Q. So how do I get Q?
Q is equals to negative W.
Okay, Q is equal to negative W. All right, so I need W.
Just work.
Yeah. How do I get W?
W is equal to negative.
Don't tell me negative Q.
No,
What is it?
negative integral of PDV. Integral.
Yeah, but we worked it out for this already.
NRT.
ln b final over. See, you could do the integral of PVT again, but hopefully you know this one. Right? Anybody remember that? So, I can put that into Q, I can integrate this. So I'm getting the integral. Notice there's no change in temperature, right? So I'll end up losing the integral. So I get an nRT ln b final over v initial. There's no dt. The t's canceled, so this is just all a constant. nR ln b final over v initial. So that's the entropy change from an isothermal.
Is it negative? Up top?
This negative cancel that negative.
Oh, yeah.
Right.
Let's say we memorize that part. If we memorize, does that apply to every isothermal?
Every
part?
isothermal, yeah.
So the best thing for those systems, whether it's isothermal or whatever, is to memorize like what those works equal. Like,
Yeah, those works are super useful. Yeah, the works, the delta U, the Q's, yeah, you want to know those. Because when you do your engine diagram, you got to know exactly. Let's do another process. Let's do, how about CP? Right? Constant pressure. ISO what? ISO baric. That means delta P is 0, right? So I got a P naught, that doesn't change. Got P naught, but I got a V naught and a V final. Right? Like that. Does that make sense to everybody? Okay, we're going to do the same thing. Let's calculate the change in entropy. Oh, on this list here, right, this list of state variables, you can add S. S is a state variable. That means what? Doesn't matter how you get there, right? It just depends on the change. But it's weird because we calculate using how we get there. So that's weird. Right, how do we calculate delta S? dq of t. Q depends on the path, but S doesn't. So that's kind of an interesting thing. Okay, so what do we know about isobar? Delta P 0. Somebody give me something else. What's work?
Negative P times the change in volume.
Negative P delta V, right? Not 0. That's isochoric. What else? What is Q? What's Q?
NCV or C sub V, change in temperature plus P times change in volume. Oh, wait,
Yeah, just
I'm getting
NCV
it
delta T?
wrong. Yeah.
Yeah, CV is times R, right? Anybody remember this? Isn't that it?
Oh yeah, I think it's CP. Yeah, it's
Yeah.
CP.
Oh, I did the wrong one. Thank you.
How would you know that it's CP or CV?
Constant pressure.
Oh, there you go.
Constant pressure. The other one's CV. Okay, so what is DQ then?
CP is 5 half star.
This should be CP is 5 halves, right?
Yeah.
Yeah. I'm a little out because I was like, kind of half dead on Wednesday. That was rough. All right, so we got to calculate delta S, right? So delta S equals the integral. So dq is going to be in terms of dt, so t naught to t final. dq is going to be ncp dt over t. Right? Everybody see how I did that? Because dq is ncp dt. So that's just what? ncp integral of dt over t is ln t final over t initial. And you can do CV, you'll get, instead of CV, you'll get CP, you get CV, right? If you did the other one. So that's pretty easy. That's the volumetric. Yeah, the weird one's A to B attic, but you could do it. In the interest of time, I won't, but you could figure it out. So you can calculate the process, right, for each of these. Okay. Okay. So this is the idea. Right? How do you calculate entropy change? But this doesn't tell you what entropy is. So now I'm going to tell you the truth. Right? Entropy, the correct definition. I don't know if you guys are excited. I'm excited.
I'm excited.
Thank you.
I thought you were gonna hit us with it actually doesn't exist.
I've been leading you on here on how to calculate entropy change, but I didn't tell you what it is. That idea of disorder is just an analogy, it's not true. First we have to define a quantity called W, which is the multiplicity.
Why did you so many W's?
Mm-hmm.
I don't like it either. When I was in college, we didn't use W, but now they use W.
What did you use?
You want to use what I used?
Yes.
We use capital Omega.
Okay, that works.
That's fine.
So capital Omega, like ohms, like the ohm sum, you know, for ohm. I like that better, but your book uses W.
The book can go from
Exactly, that's what I'm saying. Okay, so multiplicity. This is the number of microstates for a given macrostate. What the heck does that mean? Okay, let's define macrostate. Macrostate is given by the state's variables. So if I want to know the macrostate of a gas, I need to know its pressure and volume, which would then tell me its temperature, its internal energy, its entropy, right? So the macrostate is determined by the state variables. Okay, make sense to everybody? Let's look at a gas going on the simulator. Okay, there's a gas, right? Pressure, volume, temperature. I have a macrostate. The microstates is basically what you would do is you would make a giant table. So you'd number all these particles. Particle 1, 2, 3, 4, 5, 6, and particles. Right, a bunch. And then you would have a table of x, y, z is x, y, z coordinate, and is momentum in those three directions. So you would have a table of each particle, 6 numbers for each particle. That describes the microstate. Okay, does that make sense, everybody? Now looking at this gas moving,
So
yes,
the microstate's position and momentum for each particle.
for each particle. But notice what's happening to these particles. Are they staying still?
Nope.
No. And is their momentum the same all the time? Right? So the microstate is always changing, but notice what's not really changing. Pressure, temperature. There's a whole bunch of microstates for that one macrostate. You see what I'm saying? That's what we define multiplicity as. How many different ways I can arrange these numbers in here to get the same pressure, volume, temperature?
That's insane.
That's insane. That's a big number. It's a big number. That's called the multiplicity. Okay, what does that got to do with entropy? Entropy, S, is Boltzmann constant. Remember we talked about Boltzmann constant? Times the natural log of the multiplicity. That's the definition of entropy. So put triple equals there. That's how we define it. k times the natural log of the multiplicity. And the multiplicity is just the number of ways I can arrange the particles for a given state. Okay.
What was K again?
Boltzmann constant.
Yeah, but like what was it?
I don't remember the number.
And
Eight.
we won't need to remember that.
No, I'll give you the number. It's 8 point something.
Something.
I don't know. It's just
There was a couple though. There was the Boltzmann and then there was
the gas constant. The gas constant is 8 point something.
yeah, the gas constant.
Yeah. But I'll give you those on the test. You should know CP and
I think
CV.
it was 1.032.
That's probably what it is. Yeah, I was giving you the gas constant. What are the units? Joules per Kelvin. That's the units for K. The Boltzmann constant is joules per Kelvin. This is dimensionless. Multiplicity is just a counting, so it's dimensionless. Right? Okay, this is hard to fathom. Trying to count all these. So let me give you another way to think about it.
Yeah, right. Like, would that even be possible?
Yes, but not easy, but possible. I'll show you it in a minute. An analogy here is dice. Right?
It's like probability.
It's like probability, yeah.
It's like quantum numbers.
Probability was fun.
Yeah, it is. You're exactly right, Mary. You actually yes, quantum is important. We're gonna see in a minute. We gotta try to get this all done as quick as we can. So, this is an example to help us visualize, but this is not a true definition, right? Because we're rolling dice. Dice aren't molecules. But it's an analogy so we can picture what's going on. So, let's say my dice, the macro state is the sum of the two dice. That's what I can measure. I roll two dice. I don't know what one dice says or the other. I can only read the macro state, the sum of the two dice. But there's different ways to get that sum, right? So, for 2, there's one way. But for 7, there's 1, 2, 3, 4, 5, 6 ways to get 7. So the multiplicity of 7 is 1, 2, 3, 4, 5, 6. And the multiplicity of 2 and 12 is 1. Right? Did you see how you get the multiplicity? How many ways I can get that state? And then to calculate the entropy, I would just take S equals K times the natural log of that multiplicity. So 2 or 7 or whatever, 1. Right, that allows me to calculate the entropy. But it's just calculating the multiplicity. I'm just converting it to the correct units with the Boltzmann constant and bringing the number down with the natural log. Because natural log takes big numbers and makes them smaller. Okay? So that's what entropy really measures. Okay. Now you say, Dr. Browning, how is that possible with a gas? Oh, you have my phone. So, there is a formula. I don't have it memorized. I know I have a lot of formulas memorized. It's in here somewhere. I just gotta look it up. Okay, hold on, let me look it up. There's the formula.
Oh my god.
The entropy of an ideal gas equals NK, the number of molecules times Boltzmann constant. Let's make this bigger.
Do you have to know this?
No, I don't even have this one memorized.
I know, so.
Right? Times the natural log of V over N times 4 pi M, the mass of the molecule, divided by U, or times U, the internal energy, divided by 3 n H squared, Planck's constant. To 3 halves plus 5 halves.
What's N again?
N is the number of molecules. This is how you calculate the entropy of an ideal gas. You can calculate that. You have to know quantum mechanics to calculate it. But that's what it is. So when they first discovered entropy, they had no idea about quantum mechanics. This is before quantum mechanics. They knew they were calculating the change in entropy, but they had no idea what they were actually calculating. Because they didn't have the concept of multiplicity of the number of states.
Based on the formula that you gave us with the whole Vn times 4 pi everything, would that be the multiplicity? Essentially.
Yeah, so if you take this e to the exponent of this, you would get the multiplicity. Right? Because the K, so, right, K natural log of the multiplicity, so ignore the K, and then you gotta bring the N up here. Well, you gotta multiply the N through, and then take e to the, and then you would get the actual multiplicity of an ideal gas. Right, you can do it. That's for thermal, when you take thermal.
Have you memorized that, or did you just like forget it?
Huh?
Did you memorize?
Oh, I've used it on a test and stuff when I was in college, yeah.
Okay.
But I don't use it every day.
Yeah. Wow, I assume not.
But let's see if it works. Let's see if this works. Let's do the delta S again for an isothermal. So an isothermal, delta T is what? 0, right? So I want to calculate delta S for an isothermal using this formula. P naught, B naught, P final, B final. Okay?
You need a number of moles.
Yeah, we need, well, NK is equal to NR, right? So NK equals 1 NR. So that's in molecules or moles, so that doesn't matter. We can leave NK and then convert to NR. So let's do that. So the first thing we gotta do is, I gotta do this, to get delta S, I gotta take S final minus S initial, right? So that means I'm gonna have to put in B final and B initial. But luckily, I can use a property of log to make this easier. Log of A times B. How can I simplify that? Log of A plus log of B, right? So I could write this as S final as NK, and then you see ln of V plus ln of all this other stuff, right? But that stuff doesn't depend on V, just the V. You see what I'm saying? So I have V times all this. So this is A, this is B, plus the 5/2. And then we're going to subtract, this is V final, subtract NK, ln of V naught, plus ln of all that stuff, plus 5/2. Right? This is the same, isn't it? Because this what? This only depends on U. Right? It doesn't depend on V.
Because the temperature's constant.
Because it, right, that's why I picked it. It made it easy. If temperature wasn't, then I have to put it in, but I'm trying to make it easy. And then the 5/2, that's the same. So these all go away. So I get delta S equals NK ln of V final minus ln of V initial, which is NK ln V final over V initial. But NK is NR ln V final. It's the same formula. Okay, so I use the actual definition of entropy for an ideal gas to get that. So it works. Okay, now are you ready for something really crazy? I think we have time to do it. What? I'm good, thanks. This is a great website. Have you guys ever heard of hyperphysics? It's a great website. Because it has lots of cool physics. Demonstrations, formulas, explanations. Oh, crap, I don't want that back. I still got it. Okay, I need a white screen. Okay. All right, so now that we know what entropy really is, now we can learn what temperature really is. Right? Because what was it? What did you learn temperature was in grade school? What? Measure of heat. Okay, that's actually a really bad definition. Sorry, grade school lied to you.
Measure of agitation of the molecules.
Yeah. So random kinetic energy. That's a little better. How hot something is, because heat's really transfer of energy. So they got that definition wrong. Sorry. It's okay, but I'm going to tell you what it is. Remember, we define things with what in physics? Formula, right? So 1 over T is equal to the partial of S with respect to U. That's the definition of temperature. What is it? It's related to how the entropy changes with the internal energy. Yes.
When you wrote that, my brain went back to physics 1, where it's like 1 over t equal to f, the frequency.
Oh yeah, different T though.
I was like, no.
That was period. So this is the true definition. Okay, so it's the rate of change of entropy with respect to energy. Let's see if we can use it. So let's go back to an ideal gas, which I lost. So I gotta pull it up again.
Is that with the triple equal sign?
Yeah, that's definition. Let's go back to the ideal gas entropy here. S equals what? All that stuff, right? So if I take S with respect to U, let's see what we get. Because it should give me 1 over T. Right? Let's see. So this is S. I want to take the derivative with respect to U. So again, I got to do that thing I did. So S equals NK. So now I want ln of U, right?
Mm-hmm.
So you need ln of U to the 3/2 plus ln of everything else, right? Plus 5/2. Do you see what I did? I broke it apart just like A plus B, right? But this time I want U to the 3/2, and then all this other stuff is in here. Now I want to take this, the derivative of this with respect to U. The internal energy. Okay. Okay, so take the derivative, we get partial of S with respect to U equals, I can pull out the NK, and I have the derivative, or the partial, sorry, with respect to U of ln of U to the 3/2 plus dot, 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 dot. Right? Well, when I take the derivative with respect to U here and here, what's going to happen?
It's a constant.
These are constants, so there's no derivative, right? It's 0. So I just got to do this one. That's the only one I need, right? Because those are gone. So I can bring the 3/2 down, so I get NK 3/2, the partial with respect to U of ln of U, because I just brought the 3/2 down. What's the derivative of ln? 1 over NK 3/2, 1 over U. This equals to what? 1 over T. Right? Just switch the U and the T. U equals 3/2 NKT. So there you go. So that's what we had before for the internal energy, 3/2 NKT, using Newton's laws and deriving it. You remember that? And then we defined it. But this is the true definition of temperature in terms of entropy. Right? How the microstates change as you change the internal energy. Okay, you ready to blow your minds? I have two systems, right? Hot and cold. I bring them together, what happens?
Thermal equilibrium.
What does that mean in terms of all this stuff? What does that mean? If I have two systems, here's my hot system, here's my cold system, I bring them to thermal contact, they exchange energy, they stop exchanging energy when what?
When change in entropy is 0.
Okay. When the temperature is constant, which means that, let's call this A and B, right? So the partial of SA with respect to UA will equal the partial of SB, right? Because this is equal to what? 1 over TA, 1 over TB, they're equal. So the entropies are ended up maxing out. Let's see what that means in terms of the multiplicity. Okay? So how do I calculate multiplicity? right? Multiplicity, right, or sorry, entropy is K natural log of the multiplicity, right? So how do I get the total entropy? That's S1 plus, or SA plus SB, let's say, right? We just add them. So that's what? That's K natural log of multiplicity of A plus K natural log of multiplicity of B, right? Which, what happens when I can add, what happens to adding? It's like multiplying, right?
K ln of
K ln of
Omega A.
multiplicity A times multiplicity B. So this is the total multiplicity, the product of the multiplicity. It's kind of like probability. You multiply the probabilities, right? So that's what we're doing. Okay. So what happens, and I'm trying to remember that I didn't look at the algebra before I came to class, sorry. We want thermal equilibrium, and when does that occur? When these are equal, right?
So changing entropy is going to be 0, right?
I don't think so. Are they? Maybe the total.
The total, yeah.
Yeah. So we want, essentially what we want to do is maximize the multiplicity to get that. I should have looked at the algebra. I ran out of time this morning. But we want to maximize this multiplicity. That's when I get thermal equilibrium to happen. Right? So thermal equilibrium happens when I maximize the total entropy, not just one object or the others, but the combined multiplicity. So the total entropy is increased. I maximize the entropy because I maximize the multiplicity. It's not 0, it's maximized. That means if it's maximized, the derivative is, that's how it goes. So if S is maximized, the derivative of S with respect to U, right, U total, the total energy, that'll be 0. But individually, these will be equal and opposites. Yeah, there's algebra to show it to work out. It would take more time than we have. They're really cool stuff. And it gives you a whole new way of thinking about entropy, energy, and all this stuff.
So are we gonna need to be able to use these formulas?
No, this is for you to, you should be able to do the basic ones like isochloric, isobaric, isothermal processes, calculate
But
delta
not
S.
with like this stuff.
No, this is all for when you take the next thermodynamics course. We'll go into much deeper detail.
Do you teach thermodynamics?
Well, we haven't taught it yet. I'm guessing I will.
Next semester, right?
I don't know if it's on the next. It might be for you, because he's ahead of everybody. Transferred in stuff. But it'll be usually it's your senior year, because it's pretty involved. We start doing infinite sums and integrals and partial derivatives and all your calc 1, 2, and 3 coming together. So it's a lot of fun.
I thought I was done with that.
We're done with that class. Now
Dr.
you got to
Brown.
apply it.
I have a question. Really important questions.
Yeah.
So, when is going to be the review session?
I don't know. I got to talk to Mrs. Brown.
So it's not going to be tonight?
No,
right?
it's either gonna be Monday or Tuesday. I don't know. I got it.
Awesome.
Huh?
Let me push back the homework.
Sure. Send me an email. I'll be happy to push it back for you guys.
But the test is still on.
The test is still Wednesday. Yeah.
But you said this homework that we have is not going to be on the test because it's about freeze, right? You said freezer or stuff like that. Let me
I'm not gonna ask you about freezers and refrigerators.
refrigerate and heat pumps.
But this check, I'm gonna ask you about entropy. This stuff will be on there. Not this complicated stuff, but the first half of today's lesson.
But the homework that we have to do this week is about refrigerated and heat pumps, the second half, right? Isn't it?
I think so, yeah. And I'm not gonna. Right. I think it is.
And on Monday, can we ask you what sort of questions you're thinking of asking for the
Yeah.
test?
Yeah.
Yeah. Monday's meant for review.
Yeah.
So-
You